Most machine learning models are designed to give you a single, concrete answer. But what if that's not really enough? What if the uncertainty around that answer is just as important? Well, today we're going to dive into Gaussian processes, a really powerful way to not just make predictions, but to actually understand and model the uncertainty that comes with them. So, let's get right into it.
Think about it for a second. Most models, they're trained to find that one definitive line, that single right answer. But what if the uncertainty wasn't just some annoying noise we're supposed to filter out? What if it was a core part of the story the data's trying to tell us? What if you could actually model the shape of what you don't know? That is the big mental shift that Gaussian processes bring to the table.
Okay, so here's the crucial difference, right? A traditional model, you feed it data and it spits out one single best fit function. It basically says, here you go, this is the answer. But a Gaussian process, it does something completely different. It looks at that same data and gives us an entire distribution of possible functions. It's not just one answer, it's a whole universe of possibilities that are consistent with what we've seen.
Now, that formal definition, yeah, it sounds like a real mouthful. I get it. But the main idea, the part you really need to hang on to, is that we're not just dealing with probabilities of single numbers anymore. We're defining a probability distribution over entire functions. So every time we draw a sample from our model, we're not getting a point. We're getting a whole new complete function.
And this is a fantastic way to picture what's happening. Instead of trying to nail down that one perfect curve, we're sampling lots and lots of different possible curves, and they all come from the same family, the same distribution. It's kind of like having a recipe for a type of function, and every time we cook it up, it comes out a little different, but it still shares those core family traits like smoothness or general shape.
So how does one of these things actually learn from data? Well, it all comes down to updating our beliefs as we get more information. It's a classic Bayesian idea. We start with what we think is possible before we've seen any data, and then we refine that belief into what's actually probable after we've seen some evidence. And that starting point is what we call the prior. This is basically our belief before we've seen a single data point. Think of it as a completely open mind. We usually start by saying, well, the average function is probably just a flat line at 0. But, and this is the important part, we have really wide uncertainty. We're saying almost anything is possible at this stage. This is what that field of possibilities really looks like in practice. You can just imagine countless different functions, all wiggling and weaving across the graph, within those gray uncertainty bands. Before we've seen any real-world data, our model considers every single one of these functions to be a possibility. It's just pure, unconstrained potential. Okay, now this is where the magic happens. We've got our wide-open prior, the sea of possibilities. Now we're about to introduce our very first piece of evidence, a single observed data point. Ready? Watch this. And boom, just like that, we get the posterior. This is our updated belief. The model instantly adapts. It now knows for a fact that whatever the true function is, it has to pass directly through that point we just showed it. All those other possible functions that don't, they get thrown out. And you can see how our uncertainty right around that point just collapses to 0. And it doesn't just stop there. As we keep feeding it more observations, one by one, our posterior distribution keeps getting sharper and more refined. You can see the uncertainty gets squeezed out in the areas where we have data, because we're more confident there. But look at the gaps. In the regions where we haven't seen anything yet, the uncertainty stays wide. It's so intuitive, right? The model is basically telling us, I'm confident here, but I have no idea what's going on over there.
Okay, so how do we control the shape and the behavior of all these functions? How do we tell the model what kind of patterns it should be looking for? The answer lies in the real secret sauce of Gaussian processes, something called the kernel. You can think of kernels as different recipes for functions, and they give us this incredible power to bake our own assumptions and domain knowledge right into the model.
Let's start with the absolute workhorse of kernels, the RBF, which stands for radial basis function. You might also hear it called the squared exponential kernel. Honestly, this is the default choice for so many problems, and for good reason. It's incredibly flexible. Its main superpower is producing these wonderfully smooth, infinitely differentiable functions. The core idea behind it is pretty simple. Points that are close to each other should have very similar values. As points get farther apart, their influence on each other just drops off. So if you expect the underlying pattern in your data to be smooth and continuous, the RBF kernel is your best friend. But what if your data isn't just smooth? What if it repeats itself over and over again? Well, for that, we need a more specialized tool. And that brings us to the periodic kernel. As you can probably guess from the name, this one is all about finding and modeling repetition.
This kernel is an absolute game changer for modeling anything with a cyclical pattern. We're talking about things like seasonal sales data, daily temperature fluctuations, or any kind of data with those regular wave-like oscillations. Every function it generates will have that same repeating pattern.
All right, and for our last example, let's look at maybe the simplest recipe in our cookbook, the linear kernel. But don't let its simplicity fool you, because it's fantastic for modeling the bigger picture.
This kernel does exactly what it says on the tin. It generates straight lines. Each sample you draw from a GP with this kernel is just a line, with a different slope and a different intercept. Now, on its own, it might seem a little basic, but it is incredibly useful for capturing those overarching global trends in your data.
Now, here is where things get really powerful. We aren't stuck using just one of these recipes. We can actually combine them. We can add them, multiply them. It's a process sometimes called kernel engineering. It's like being a chef and mixing different ingredients to create a totally new flavor. So let's see how we can use this to model something a lot more complex. All right, let's put this to the test. Imagine you're handed this messy, noisy data set. You can tell there's some kind of pattern hidden in there, but your job is to uncover it using only these scattered data points.
So how are we going to solve this? Let's try out our different recipes. First, let's just use a periodic kernel. And, well, you can see it captures those oscillations pretty well, but it completely misses the obvious upward trend. The whole thing is drifting upwards. Okay, so that's not right. Let's try just the linear kernel. This time it nails the upward trend, but it's totally blind to all those little wiggles. But look what happens when we simply add the two kernels together. Bam, it's a perfect match. The model is now smart enough to see both the big picture trend and the seasonal fluctuations.
And what's so impressive here is not just that the mean prediction, that blue line, fits the data so beautifully. It's that the model also gives us these incredibly intuitive uncertainty bands. It's confident where it has data, and it's telling us it's less certain in the gaps. That is exactly what you want. So, when you put all of these pieces together, you start to see why Gaussian processes really do feel like a modeling superpower. Let's just do a quick recap of why they're so special.
So, what are the superpowers? First, you get a full distribution over functions, not just one measly answer. You're modeling the entire landscape of what's possible. Second, they naturally quantify uncertainty. The model literally tells you when it's guessing, which is absolutely critical when you don't have a ton of data. Third, kernels let you bake your own assumptions right into the model. You get to give it hints about what kind of patterns to look for. And finally, you can combine these kernels, like building blocks, to create sophisticated models that can solve problems no single kernel could handle on its own.
So the next time you're looking at a modeling problem, especially one where data is scarce or you really need to understand the what-ifs, give Gaussian processes a thought. And that leaves us with one final question to chew on. In your own work, in your own world, what kinds of problems could you solve if you had a much smarter, more principled way to deal with uncertainty?